One of the things that we study in my lab is motor adaptation. And I have some slides that actually go through that in a little bit more detail. But I want to give you guys a sense of what that means. So I met you at lunch, and you're at the end. And I'm going to ask you to come down and join me. I don't mean to put you on the spot. Are you right-handed or left-handed?
Right.
Right-handed. OK, here. You stay right. Right? All right, can you touch your nose? Good. All right, can you hit my hand? All right, good. All right. All right. So that was easy, right? That was fine. All right. Put those on. All right. Can you see me?
Kind of.
Kind of? All right. Can you touch your nose? OK, all right. Touch my hand. All right. All right. So what I want you to do, I want you to make a pointing finger right there, OK? And I want you to touch my hand. I want you to do it. Well, actually, before we do that, I want you to see it, all right? I want you to do this, all right? I want you to like basically touch my hand like this. So try it without the glasses. Go ahead. Down. When I say go, how about you do it really fast? Go. 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 All right. Put those on. All right. See my hand?
Yep.
Go. Good. Fast. Go. 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 Touch your nose. Good. Go. 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 All right, take those off. Look at me. Go. Ah, no. All right. But good, good. Give him a round of applause. That was good. All right. So I apologize for being late, but how many undergrad students are here? OK. Will somebody venture what just happened to tell us what happened? Somebody knows. They're looking at you. No? You?
Oh, right.
There?
I'm assuming that he formed new pathways to adapt to his.
Adapt is good.
Compensate for his different range.
Yeah. Yes, that's closer. So first these are prisms, all right? So they're shifting your vision by a certain angle, and you're not used to prisms, right? So you're trying to match what you see to the outcomes of what your movement actually resulted in, and over time you're adjusting your motor commands basically to adjust for that visual shift. Now, why is it when he touched his nose, it didn't matter? Because it's on his person, right? So it's not like you're planning it in extrinsic space. You're planning it based on your body space. What I want to talk to you about is human motor control studied through the generalization of motor adaptation. A lot of things that I'm going to talk about have basically been introduced already. So there's going to be some themes that are kind of repeat. So, quickly, this is my research group at George Mason. We conduct translational research investigating basically sensorimotor integration, so visual perception, motor learning, I have that highlighted for a reason, retention, control, and we use computational, experimental, and behavioral approaches to basically study that. Now, I highlighted motor learning because that's what my talk is basically going to be about, motor learning. So what is motor learning? So motor learning is the acquisition of novel motor skills. And my video has disappeared. That's weird. That didn't happen before. Oh, there we go. OK, good. All right. So this was a high school student, Nick, who volunteered in our lab last summer. And the question we asked is, well, how long does it take to learn how to juggle? OK? So the first day, right, on the left, you can see that he's not really confident in where those balls are as he's trying to throw them up in the air. And he can really only get through one cycle. And by the 22nd day, he's much better, all right? So he's basically acquired a new motor skill. Now, in our lab, we don't have 22 days to basically monitor someone's progress in a motor skill. So what we look at is motor adaptation, which is a much shorter form of motor learning. So what is motor adaptation? Motor adaptation is a form of motor learning. It's a short-term updating of internal models. So that's exactly what you experienced when you came down here, right? a system that predicts the sensory consequences of our movement. And that demonstration that I did in the beginning was basically a demonstration of the updating of this internal model. So you experienced some errors, and you basically adjusted your motor movements to basically reduce those errors. Okay? Now, why study motor adaptation? So why study these short-term forms of motor learning? Well, they give us insight into basically how we learn to move, right? So when you're a little baby and you're trying to take a Cheerio from your sister, hopefully not knock the bowl of Cheerios on the floor, you have to learn basically how to make those kind of goal-directed movements. It's also important for giving us insight into rehabilitation. So if you suffer from some disease or some kind of injury, how do you basically get the motor system back to the normal states? And then also, how do you get beyond those states? So when you talk about superior athletic ability, you're talking about like fine-tuning the motor system. So it's a heightened sense of, I guess, motor learning. So that's why studying motor adaptation is important. And there are several ways that we study motor adaptation in our lab. One you've seen, one you haven't seen, which I'm going to talk about today. So the one that you haven't seen is adaptation to novel movement dynamics. So we have people come in, we have robotics that they interact with, and we look at their compensation to physical perturbations to their movements, right? The other way we do it is by altering the feedback they receive. So much like these prism glasses that he wore, we can look at how people basically adjust to these errors that we induce visually, right? And the thing that we ultimately try to do is try to capture this process with math, right? So we try to apply engineering principles, equations, to basically understand the kind of algorithms the brain is doing and trying to solve these kind of problems. Does that make sense? I'm going to continue to look at you to make sure that everyone's like at least somewhat nodding, that things make sense. Okay. So, adaptation of reaching movements. So we use robotics to basically look at these kind of adjustments to motor commands. We have people come in, they grasp a robotic manipulandum, so a robotic handle, and they make planar movements in this two-dimensional space. And we basically look at 3 different kinds of movements. So one are null movements. So in this case, the robot motors are turned off. The robot's basically letting you passively move its handle back and forth between, let's say, 2 targets. More interesting movements are when we actually apply some kind of perturbation. So in this case, it's called a force field perturbation. And basically, the robot will apply an orthogonal force that's proportional to some parameter of your movement, in this case, the velocity, so how fast you're moving. It'll be orthogonal to the movement vector, and it's going to push the subject's hand off that straight path, all right? So you can see that those black arrows represent the robot force that it's applying to the subject. You can see that the largest force is right here in the middle of the movement, where the peak velocity, where you're moving the fastest between these 2 points, all right? The third and final movement are these force channel movements. So these force channel movements, the robot applies basically a stiff spring and forces you to move straight. And you may wonder why that is or why that would be important, but by making you move straight, we can measure how much force you're exerting on the robot. And that will give us a quantitative idea of your ability to adapt to these kind of perturbations. Okay? So, just wanted to go through the movements a little quickly to give you an idea. So these are null movements. You're going from one target to another. The red circle represents the subject's hand. And when you make these point-to-point movements, you typically have a nice, smooth, bell-shaped curve. So there's a nice acceleration, nice deceleration. And subjects can do this fairly easily. And here's just a short movie to show you that picture progressing. So subjects start to move, accelerate, decelerate, and terminate their movement in the target. Simple. It's easy. Here's a force field movement. So here's where the subject is actually experiencing some perturbing force that the robot's imposing as they're trying to move straight, okay? So you can see that the movement trajectory is not straight. It's being pushed off. And if you look at the movement velocity, you can see that they're doing some accelerating, decelerating again, and basically trying to get the cursor back into the target. And that's what this movement looks like. So So they start to accelerate, robot starts to push them, they come back again, and eventually, eventually they land into the target. Now, that's that first movement trajectory, let's say at the beginning of training. So when we first apply this perturbation, the subject experiences over many trials, and over those trials, he starts to push back, right? So his movements become straighter and straighter and straighter. Now, the problem with analyzing just this trajectory data is that you have a lot of feedback. So you don't really know if the subjects actually are adapting to the temporal force that we're applying to their hand. So you need some other way of actually quantifying that. And that's why these force channel trials are necessary, all right? So the force channel trials makes you move straight between these targets. And as you move straight, we can measure the force that you're exerting on the robot as it's making you move straight. So what that means is that we can get an idea of what the robot pattern of force would have been. If you flip that, ideally you should be countering with this thick black line, and then this blue line is the actual force that the subject exerts. All right? So that gives you a measure of if they actually are learning the temporal pattern of force. And the movement itself doesn't look all that interesting, but the force profile actually is. So what this is showing is that subjects aren't just exerting some arbitrary force at some arbitrary time. They're actually exerting the force based on how fast they're moving, all right? And like I said, if you look at the force pattern, the blue guy, compared to what they ideally should do based on how fast they're moving, you can plot these against each other, right? And then you can do a simple linear regression to find the slope. And that slope gives you an idea of how much or what percentage they're actually compensating for this perturbation. So in this case, the slope is 0.8. The movement speed is about 0.3 meters per second. So their adaptation coefficient in this case is 0.24. Now, the only reason I bring all this up is that this gives you an idea of how you can basically quantify generalization. So we can use this analysis to examine the generalization of their learning. So you have people learn some specific task, and you can then see if you give a different context or a different set of parameters that they have to apply this in, how well do they do that? So briefly, what is motor generalization? So generalization is the ability to apply learning for movements made during one set of states. So let's say a certain movement speed, a certain movement direction, a particular arm, let's say your right hand, and how that transfers to untested states. So different movement speeds, different arms, okay? So I like this example with Einstein riding his bike because, if you learn, two wheels, how easily can you transfer that learning to one wheel, right? Probably not very well. But in this task, we can actually gain insight into the kind of ways that your brain can actually store and basically acquire those kind of motor memories, all right? So this represents the different ways that you can basically transfer learning from one set of states from let's say a slow movement speed to faster movement speeds. So in one way, could just be a very simple linear extrapolation. If you move faster, you're going to apply more force because you've learned what the trade-off is, right? You've learned basically if I move at this speed, I apply this amount of force. If I extrapolate that out, if I move faster, I should exert more force, right? Another way is that there's some kind of cap on how much you learn. So if you only learn up to this point, even if you move at a faster movement speed, you're only going to exert that much force. So if you look at the actual force profiles, you get something kind of weird in the sense that once you get to a faster movement speed that you haven't experienced, you're not going to exert any more force, or you're going to scale this whole force profile, this whole temporal pattern of force down to some level that you only experience during training. The last way is, let's say, once you get past the movement speed that you experienced, it decays in some Gaussian way, so it exponentially decreases. So in that case, you also get something somewhat unrealistic in the force profile that as soon as you start to move faster, you're actually going to decay the force exponentially of how much you're going to exert, okay? So you can actually make these predictions and then test and see, well, how do people actually generalize? How do they actually transfer what they learned from one state to faster states, to states that they hadn't experienced yet. And we conducted a very simple experiment. So we had some baseline trials where we got an idea when people moved at a slow speed or they moved at a fast speed, okay? Some baseline measurements. Then we actually trained them in this adaptation at the slow speed. So they only experienced this perturbation for the slow speeds. And then we tested them at slow and fast speeds to see how much of this learning here did they transfer to these faster movement speeds. So this is a force pattern at the end of training. You can see that they match the force profile fairly well. Here's at the beginning of this testing period, again for the slow movements. And again, they've basically retained that, that mapping between the force that they should exert and the speed. If they were going to do a linear extrapolation, you would expect to see a thinner and taller force pattern, right? And that's exactly what they do. So there's a linear extrapolation of what they learned for those slow movement speeds to these faster movement speeds, right? You can look at this in more depth. I don't know if I have enough time now, though. No, I'm way over. Okay. I have time? Okay. So you can look at these in more depth. So if you look at all your subjects, which is represented by these black dots, so this is the movement speeds that they moved at. This is that raw adaptation, that adaptation coefficient. If you bin this data by speed, you can see that even during training, the faster they moved, they exerted more force. If you just take this bin data, you can fit a linear extrapolation of that. So if they generalize linearly, it should fit along this line. If they basically do some kind of level transfer, it should fit this line. And if it's an exponential decay, it should fit this line. If you look at the first movement during the generalization case, it's right on that linear extrapolation. If you then look at the next subsequent movements, you can see that there's a steady decrease of the force that people exert. So they're actually losing some of that adaptation that they're transferring. And it turns out that the decay of that adaptation closely matches the decay that you would see at the trained movement speed. So the red guy are these faster movement speeds that they hadn't experienced during training. The blue guys are the slower movement speeds. And the decay of the adaptation for both cases is exactly the same. So there's a constant extrapolation to these novel movement speeds, even though they hadn't experienced them yet. You can also make predictions on, is the force that the subjects exert, is it linear, is it close to the linear prediction, or these other two predictions? And you can see that there's a significant difference between these other two predictions. So therefore, you can rule those out. You know that they are linearly extrapolating their learning to these movement speeds. So that was the brief, hopefully, part of what we do in my lab and the kind of things that we study. The students, Egbal and Katrina, are following up on this. Nick was the high school student that was doing the juggling. In the beginning, a lot of my part of my research is being funded right now by the I Institute, the institute that I was actually here doing research for my postdoc. And do I still have more time? I hope. Quickly. Yeah. Good. All right. So, unsolicited advice. All right. Find a place that makes you feel at home. So, if you're going on to graduate school, it's important that you find a place that you feel comfortable being. All right. That can do, that has people doing the kind of things that you want to do. All right. So one of the reasons I went to Hopkins for graduate school is because there are people that were doing these kind of motor adaptations, these kind of studies of motor learning, and they wanted me to be there. They were actively, happy that I was applying, happy that I was gonna come there and study. You should consider George Mason, please. All right. So there's a little bit of traffic in that map that I brought up, but anyway, it's only 31 minutes away, all right, from the NIH. So there's a lot of things that I'm currently doing at George Mason that involves the NIH. So that having the close proximity is really nice. There are a lot of other national labs in the area, which makes it a really unique place to do research. And it's a great school, so please check it out. if nothing else. I hope my presentation at least has George Mason stick in your mind at some point of like, maybe I should think about going there, or at least think about applying there for graduate school. Okay. Take more math than is required of you, right? So when you go to graduate school, they're going to tell you, you need to take, a certain number of math classes. And what I would suggest is take more than that, all right? Now, when I was growing up, well, actually not even growing up, I still am a big fan of The Simpsons. I love The Simpsons. And, it's a very silly show, but occasionally, their quotes that you can get are kind of interesting, right? So if you think about this one, the one on the left, facts are meaningless. You could use facts to prove anything that's remotely true, right? That's more of, I guess, statistics. The one on the right, probability. People can come up with statistics to prove anything. 40% of all people know that, right? So, if that sounds silly, then, you have an idea of why math is important, right? I mean, like people, scientists, some papers that you can probably find where people misuse statistics and probability all the time. And having a strong grasp on probability and statistics, or at least math in general, can help you avoid doing these kind of things, okay? All right. Yeah, it can only make you a better scientist. That's the bottom line. All right. All right. Last thing. So find a good mentor. So I thought Monique did an excellent job of talking about all the different people throughout her different stages that kind of guided her and gave her advice. And my one slide is not going to do justice what she already basically told you. But I can't stress enough to find a good mentor. So when I was here, I worked for a very, very famous neuroscientist, Dr. Bob Wertz. And, when I first started, I was very intimidated because, again, he's very famous, very well known. But he was an excellent mentor. And the things that you should look for an excellent mentor are some of these points. So, one, someone who will not just teach you how to do experiments. All right? For the most part, anyone can teach you how to do experiments. But someone who basically can teach you how to do science. All right? How can you think about a problem? What are the different approaches that you can take to solve that problem? Someone who will give you opportunities to succeed or fail. So there are plenty of times where I went to Bob and I said, I'd like to try this. And typically he would say, that's fine, try. And then it would not work, and that's fine, right? But at least he gave you the opportunity to find out if it worked or not, within reason. I mean, obviously you can't go out and do crazy things, but it should be someone who has the flexibility to give you the opportunities to basically find out for yourself, all right? And last thing, someone who's interested in your career and success. I thought Monique did an excellent job of describing this, but you should have conversations where it begins with, this would be good for your career. Have you thought about what you're going to do after you leave? Those are the signs of a good mentor. And now I'm done. Time? Okay.